Hey everyone, welcome back to Tech Adventure. We will continue our journey into the field of embedded and software development skills. In today's video, we're going to dive deep into the design phase, one of the most important steps in the software development lifecycle. Once the requirements are clear, this phase is all about transforming those requirements into a technical blueprint that guides the entire development process. By the end of this video, you'll learn what the design phase, overview on high-level design and low-level design, few real-world examples, and more. So, let's get started by first understanding the goals of the design phase in SDLC and how it sets the stage for the success of your project. If you missed our previous video, I strongly encourage you to check it out first. It's an essential part of our learning journey and will ensure you're fully up to speed and on the same page with the rest of the content. In our previous video, we explored the first step, planning, requirements, and analysis of software development lifecycle, SDLC, in detail. Software development lifecycle methodologies and models have several steps. These steps form the backbone of software development, ensuring a structured approach to creating reliable, high-quality software. And today, we'll be diving into the second key step, design. The software design phase in SDLC is a critical step where the overall system architecture and detailed design of the software are defined. This phase transforms high-level business requirements into a structured technical blueprint that guides the development team through the coding and other phases, ensuring that the final software is functional, efficient, and maintainable. Key objectives of software design in SDLC is 1. Translate requirements into design. Transform the business and technical requirements gathered in the previous phase into a structured design that guides developers. 2. Define the system architecture. Determine the overall architecture of the system, including how different components will interact and how the system will meet both functional and non-functional requirements. 3. Ensure quality attributes. The design must address quality attributes such as scalability, performance, security, and maintainability. 4. Guide implementation. Provide a clear and detailed blueprint that the developers will follow during the coding phase to avoid confusion or misunderstandings. There are two types of major design in the software design phase. 1. High-level design, HLD. 2. Low-level design, LLD. A high-level design, HLD, document serves as a blueprint outlining the overall structure, components, and relationships of a system, platform, or project. Its purpose is to provide a clear and concise overview of the system's architecture, key functionality, interfaces, and major design decisions. A low-level design document provides detailed specifications for the implementation of a system, platform, or project. It covers technical details such as physical data models, integration or data flows, algorithms, and platform. Please review the key differences between these two design methodologies to gain a clear understanding of their roles and applications. High-level design. HLD provides an abstract, top-down view of the system architecture. It defines the overall system structure, modules, and how they interact. This stage focuses on the system's functionality and components, providing an overview without delving into detailed implementations. Low-level design. LLD focuses on a more detailed, bottom-up approach, describing the internal structure and design of individual modules. This includes defining algorithms, data structures, and specific logic required for implementation. It serves as a blueprint for developers to write the actual code. By understanding both design types, you can better appreciate their unique contributions to the software development process and how they work together to create a complete system. Example of HLD in a real scenario? Let's take an airbag control unit, ECU, as an example of an embedded system. Here's how HLD would work. 1. System architecture consists of components like crash sensors, control unit, microcontroller, inflator mechanism, and communication interfaces. And there's interactions. 2. Module breakdown. We can further break down the modules based on functionality, like decision-making module, airbag deployment module, communication module, and so on. 3. External interfaces. Identify interfaces like interfaces with sensors for real-time data input and with car systems to communicate crash data. 4. Security architecture. Ensure secure communication between the ECU and other car systems to avoid interference. 5. Technology stack. Identify critical technology stacks like microcontroller, sensors, communication protocol, and so on. 6. Deployment architecture. Plan the deployment as airbag ECU is an embedded system deployed inside the vehicle, directly connected to crash sensors and the car's main control system. In similar way, let's see what comes under low-level design. We will take same real-time example airbag ECU. LLD translates the blueprint created in HLD into detailed specifications that developers can directly use to write code. It provides all the necessary information needed to implement each component, ensuring that the system functions as designed. LLD consists of 1. Detailed logic for components. Each module or component is broken down into its internal logic, functions, classes, methods, and data flows. 2. Detailed design of class and object. Includes detailed design for each class, including attributes, methods, inheritance relationships, and interactions between objects. 3. Interface specifications. Defines the detailed design of internal and external interfaces between modules or components. 4. Detailed state and behavior. For systems that involve state machines or specific behaviors based on events, LLD defines the states, transitions, and the logic for each transition. 5. Error handling and exceptions. Defines how errors and exceptions will be handled at the detailed level. 6. Function or method design. Breaks down each component into individual functions or methods with detailed input-output, parameters, return types, and expected behavior. If you're enjoying the video, please consider giving it a thumbs up and subscribing to our channel. We value your input, so feel free to share your suggestions for topics you'd like to see covered in the comments section below. The design phase is extensive and requires a great deal of detail, as we are essentially creating the blueprint for the entire project. This blueprint consists of several design diagrams, which are represented using UML. Given the depth of this topic, it deserves its own dedicated video. In our next video, we'll dive deep into the various UML diagrams and how they're applied across different design methodologies. We'll explore when and why to use each diagram, helping you choose the right tool for every design scenario. That wraps up our overview of the design phase in the SDLC. As you can see, this stage is crucial in laying the foundation for a successful project. We've covered the key elements and the importance of creating a detailed blueprint to guide implementation. In the next video, we'll explore UML diagrams in depth so you can better understand how to represent your designs effectively. If you found this video helpful, please like and subscribe, and hit the notification bell so you don't miss out on future content. Thanks for watching, and see you next time.